We are going to talk about momentum and forces. How many of you guys, I know Jerry teaches it, how many of the rest of you guys cover this? Do you teach physics?
Yeah. Tech ed.
Yeah. Okay, and then what you guys, and this side of the room, anybody? Okay. All right. What's tech ed?
Technology education.
So it's like physics?
Yeah.
Okay.
There's a lot of physics involved.
Okay. But it's like useful physics? Is that the goal?
Yes.
Okay. Not that it's all not wonderful and useful, but okay. We're going to talk about Newton's third law. And to talk about forces, we kind of have to hit on the first and second law, the F equals ma. So we're going to talk about collisions, and then from collisions, we're going to go into momentum conservation. So if you've got some good input on stuff you do in the class, by all means, share it with us. Okay. All right, so this is where it shows up in our standards. And the new Keystones, there's no physics one. Yeah, I know, it's very sad. They've got the biology now. Chemistry's in a couple years, I think, right? They might, but the physics is nowhere on the horizon, so it's very sad. So these are from our old standards. What's that?
The engineers are in trouble.
They are in trouble. I guess we just don't need them anymore. No more, yeah, because it's not on there. Are they still doing the PSSAs, or are they totally switching over to the Keystone? So high school's not going to do PSSAs.
No.
So there's no physics anywhere. That's terrible.
And they do biology.
Yeah. I'm offended.
But the
Yeah.
National Science Standards has the
Yeah,
physics
it's in there.
And I
Yep.
actually use them and combine that because they actually refer to different states. So
Okay.
you can actually combine them together.
Okay.
That's what the physics comes
Yeah, I don't know. I think it's kind of important, but
in. Yeah.
maybe I'm just, I'm subjective. All right, but currently even in the grade 1 standards, they're having to deal with the pushing and pulling. And then movement in grade 3 and grade 6. Right, by the time you're getting to the grade 10 and 12 ones, you're having to do the momentum conservation. So, which would I guess be you guys, because we are high school. All right, so we're going to talk about momentum. Momentum is our little p. I'm not sure where that comes from, probably some German word. Does anybody know what the little p is from? You'd think it'd be a little m, but maybe that was taken from mass and they just went with a p.
M too many times.
Yeah, m was used on the other side of the equal sign, so it was getting confusing. Yeah. So p is momentum. There's no useful, or one set of units for it, so we spell it out, kilograms meters per second. Right? They haven't come up with one thing to call it. So we write all that out. Our mass is usually, if we're doing it in SI, is going to be kilograms. In British units, it would be slugs, which you never ever see. You don't see slugs units. And our velocity, meters per second, right? Feet per second, miles per hour, that kind of thing. We'll stick with meters per second. We're going to try and stick in the SI units. So we're going to talk more about each of these. And then our F equals ma. And I'm using the same notes for the elementary and high school, so we're going to have to talk about a few things. This is a sum, right? This is the sum of our forces. It's not just any F, right? It's the sum of our forces. The F and the A are vectors, which we'll talk more about. But F is our force. We're going to measure it in either newtons or pounds, right? And our mass, once again, in kilograms. We're going to use kilograms. Our acceleration, meters per second squared. So how fast is our velocity changing? So 1 pound is about 4.4 newtons. So kind of give you an idea when we do things in newtons. Right, 4 of them will give you a pound. All right. So Newton's third law is that, and it's phrased several different ways depending on where you look at it. For every action, there's an equal and opposite reaction. It's the one I see the most in my books anyway. Yeah. Which tells us that for every force out there somewhere is another force that is the same size, but in the opposite direction. So equal, meaning they're the same size. So if you push on the table with a 5 Newton force, somewhere out there is a 5 Newton force that is pushing opposite of the way you pushed. Okay, so I'm going to give you guys some spring scales here. You get spring scales? Maybe we can work in twos. That might be an easy way to do this. each bag has one of each color, so we're trying to keep them that way so that we don't, because they measure different weights. All the same, regardless of who's pulling, right? So one person can pull hard, the other person doesn't have to pull this at all, and it's still the same, right? That's what we want to see.
It's equal.
Yeah, no matter who's pulling, right?
Yeah, it's equal.
Oh,
Yeah.
I thought you said, let's see if you can
I
get something.
did. Can you?
No.
There you go.
Okay. It's equal.
Good question.
No, it was a can you. The answer no is valid.
You're trying to get something different. Okay.
But see, now you're convinced that you can't. So, so we cannot get something different, right? unless we lawyer it, right? Unless we, hold on to the end that's not truly the spring, or we adjust our 0 point. In the good faith that is our physics experiment, we cannot. All right? Right, that is because Newton's third law tells us that no matter how hard one pulls, the other pulls back just as hard, right? So it's doesn't matter which one of you is pulling, the other one's going to feel the same pull. Okay? And like we'll talk about later, you may not feel like it's the same because if a car and a truck hit, certainly the car feels like they're getting the raw deal, right? But it's the same force. Okay. All right, so for the sake of those who don't do this in class, let's quickly run over our forces. Okay. Forces are a vector. When we say something is a vector, we mean it has a size and a direction. Right? So forces have to have a size, 5 newtons, 10 pounds, 100 newtons, that kind of thing. They have to have a magnitude. They also have to have a direction. We're going to simplify it. We're just going to do 4 directions. We are not going to do anything off axis, because I don't want to deal with cosines and sines and all that. So we're going to stay on axis.
Thanks.
I didn't think Jerry could handle it. So we are going to stay on axis. We simplify anything no matter what object we're talking about. It's a dot, right? So if we're talking about an elephant and somebody's pulling on it and the elephant's pulling something else, that's our elephant, right? It's a dot because most physicists can't draw. We can't do that. And if we did draw our little elephant, and he were, yeah, see, this is where it gets hairy. He's got a.
That's not bad.
The neck is what kills me. I can never do the neck, so we'll just leave him like that. He's a no-neck elephant, yeah. Oh, there you go. And he's got a little, there you go. All right. Yeah, and he's got a little tusk there. See, I screwed it up with the tusk. Now he's not cute anymore. All right, anyway, we can't draw, and the dots are easier, so we do dots. And by the time you draw on your vectors and stuff on top of him, he's just going to be, it's going to be sad. You're going to splice him. So he will be a dot. Erase him. The forces that act on him, like I said, we're going to stick with our axes. Everything's going to be on axes. The size of your arrow kind of gives you an indication of how big the force is. So if something is pushing up, that force, right, and something is pushing down, that force, this force is bigger because the arrow is bigger, right? So the size of the arrow is kind of relative to how big the force is. A lot of times we abandon that and all our arrows become the same, but they're supposed to be kind of relative to the size of our forces. The direction shows you the direction of the force. So this is our elephant. Something's pushing up on him, and something's pushing down on him. And what's pushing down on him is much bigger than what's pushing up on him. Right? If somebody were yanking him this way, right, you would draw a force that way. If there was somebody in front of him trying to stop him, right, he would be feeling a push that way. And the size of those arrows are kind of relative to how big those pushes and pulls are. Right, so far so good, right? Okay. So we're going to use the convention that these are going to be positive forces if they're up, negative forces if they're down, positive to the right, negative to the left. You don't have to do it this way. You could rotate your whole axis if you wanted to, but that's a little more confusing. So we're just going to do it this way. We're going to use this convention. We're not going to do anything on ramps either, so we don't have to worry about rotating our coordinate system. We're just going to stick with this guy. Okay. All right. So we have this other Newton's laws. We're going to have to visit the first couple laws before we're going to come back to the third law. But we have this guy, F equals ma. And remember we said this is a sum. So there's a couple different notations we can use for that. We can either write a sigma here, and that means we add up all of our forces. We can write a little net down there. It's a net force. We've added up all our forces. Right? Either one of those would work. I think I actually went with that or nothing, but it's also supposed to be a vector, right? It has a size and a direction. So we got to keep that in mind with the F and the A. Normally we would draw an arrow over them, so that tells us these guys are vectors, but then it starts to look ugly, so we're going to streamline it. All right, so our net force, our sum of forces, is equal to our mass times our acceleration. All right, so if our forces do not add up to 0, and we're going to add our forces in a second, but if they do not add up to 0, then this cannot be 0, right? If this is not 0, then we know there has to be an acceleration, right? So our object has to be either speeding up or slowing down. If our forces add to 0, so if the left-hand side is 0, then this side has to be 0. Our mass isn't 0 because we're not going to talk about objects that are 0 mass, because that would just defeat the purpose. So if this side is 0, our acceleration has to be 0. So if our acceleration is 0, what type of motion can that object have, if any?
Still.
It can be still. That is one option. It can be sitting completely still, not accelerating. Right? What's another option? Constant speed. Moving at a constant speed, because then it's not accelerating. Right? Accelerating means you have to speed up or slow down. Right? All right. So we're going to look at x forces, the ones in the x direction, which are these guys. Right? And we're going to look at y forces, the ones in the direction, the y direction. Right? So if our x forces do not add to 0, our object has to be accelerating somewhere in the x direction. Right? If our y forces do not add to 0, our object has to be accelerating somewhere in the y direction. I don't know if I have this on the slide. No. Okay. If our x forces add up to 0, that doesn't tell us automatically that it's stationary. It tells us that it could be, right? Or that it could be moving at a constant speed, right, in the x direction. If our y forces add up to 0, once again, doesn't tell us that it's stationary. It could be, or it could be moving in a constant speed. So when you see a force diagram, like if we were to show you the force diagram of our elephant, and he had, let's just do x direction, he had just 2 forces on him, and they're the same size. Just by looking at this picture, we don't know if that elephant is moving, right? If these two are the same size, they add up to 0, our acceleration has to be 0. He could be sitting still, or he could just be coasting along at the same speed, right? Not changing speed. We don't know what it is by looking at this picture, right? My students, whenever it adds up to 0, they automatically want to assume it's not moving, right? That's just the way it works. But we don't know that, right? It could be moving at a constant speed, so we're not sure what he's doing. All we know is his acceleration is 0. Okay? So if our forces in this direction add up to add up to 0, either stationary or constant speed. But if they were unequal, right? And this guy was 2 newtons, and this guy was a minus 5 newtons, right? Those aren't the same size. They're not going to add up to 0, right? So this guy has some kind of acceleration, okay? Doesn't tell us what direction he's moving in, which we'll come back to later, right? It tells us which direction his acceleration is in, but not the direction he's moving. Actually, none of your force diagrams, unless you're told, they aren't going to tell you which way your object's moving. Okay. So when we add these guys up, this guy, we would be adding 2 and a minus 5. So this guy's net force, his total force in the x direction is going to be a minus 3. Right, so we would say F net, notation I usually use is comma x, because it's in the x direction, is going to be minus 3 newtons. You could also just say F is 3 newtons in the minus x direction. You could say that. Right? That's another way to say it. What you have to remember when you're doing forces is you need a size, 3, and you need a direction, minus x. Right? In this scenario, you need a size, 3. Your direction is minus x. Okay? They'll both have to show up there. All right, so let's see. Let's make this guy 10 newtons. Let's give him another 6 newtons. You can draw forces over top of each other. Make sure you give them an arrowhead. Right? Your object is the dot. If the force is pushing it or pulling it this way, your arrow is going to go to the right. If your force is pushing or pulling it that way, your arrow is going to go to the left. Right? And then let's see. This guy, what is our net force on this guy? 1 where? Right, to the right. Right? Because we've got a negative 10, we've got a plus 5, and we've got a plus 6. Right? So that's going to give us a plus 1. So if somebody were to say, what's your net force? You would have to say plus 1 to the right. Right? Unless you've established that plus automatically means to the right, which is fine. But that's to the right. So let's see, 4, 2, I don't know, 5. Ah, what's that guy's net force? 0, right? So anything that way is a negative force. Anything this way is a positive force, right? When we're on this axis. When we're on this axis, anything up is positive, anything down is negative. So this would have been a plus 4, plus 3, minus 2, minus 5, and that's going to add up to 0, right? That scared the heck out of me. That's out of the corner of my eye. Oh my God, somebody threw something at me. All right. So I know you guys over here who teach us are fine. How about you guys over there? Except for you, the ones who don't teach us. Are we okay? Yeah? We're just adding them up along the line. Anything to the left is negative, anything down is negative, right? If they add to 0, our acceleration is 0. If they don't add to 0, our acceleration is not 0. Okay. What if we had, let's see, let's call this guy 10. Let's call this guy 8. And see, I'm not to scale very well here. 5 newtons and 3 newtons. What would our net force be here? And let's keep it in 2 dimensions. Let's not give it an angle. Okay? Yeah, look at them independently. For the x's, we would have a plus 5 and a minus 3. Right? So we would have a plus 5, minus 3. So we're going to have a plus 2 in the x direction. Right? And then we do the y separately. So for the y's, we're going to have a plus 10 and a minus 8. We're going to get a plus 2 in y. Okay? If you really wanted to, right, you could find where that lies on your axis, and you could find an angle, and you could draw it with 1 arrow, but we're not going to do that. We're going to stick to things straight on the axes. Right, for Jerry. Okay? All right. Let's see. Okay. 10 newtons, 3 newtons, 2 newtons, and a 1 newton. All right. So in our y direction, what is our net force? Negative 2, right? Because we have an 8 minus a 10. So we would have a minus 2 for our y. This is where it gets kind of weird. You can say minus 2 in the y direction. You have to realize that minus means you're down here. Or you could just say 2 in the minus y direction. Right? That'll work as well. Okay. You guys okay? Do you disagree? No. Okay. You're sitting there nodding no. All right. You like the what? This one? Yeah. Yeah. Well, I usually use I hat and J hat. So Do you guys use I hat, J hat?
What's that?
It's a unit vector. Normally, in the physics that I teach, I hat means, that literally means, that's I, and there's a little hat on him. It's a vector hat. It's a unit vector. That symbol means in the x direction. So you would have, for this case, you would have -2 I hat. And that would tell me -2 x direction. And then in the y direction, we use a j hat. That's just the standard notation for the physics that I end up teaching. So you're nodding no, you guys don't do IJKs? That would explain why when my students come to me, they don't know what IJs and Ks are. They get it in Calc too?
Or then sometimes pre-calc.
Okay, yeah, we do I hat, J hat, and then K hats would be Z, but we never do Z. Usually it's two-dimensional. Yeah, just to make it easier. Sometimes they do X hat, Y hat, but it's usually I hat, J hat. So I'm not used to either of those. But I didn't want to go into unit vectors, so we'll just erase those guys. All right, so what is it in the x direction? 0, right, because we had 3, -1, -2. So actually, yeah, there should be newtons there. I'm also very bad about my units. So 0 newtons, right, in the x direction. You could also say 0 newtons in the -x direction because it doesn't matter because it's 0. Or -0, if you really want to, but it's 0, okay? All right. Okay, so we know that F equals our sum of forces, or F net. Do you guys do the sigma or do you do F net? What do you do for sums? F net? Yeah. My sigmas end up usually looking kind of strange anyway. F net, right, is equal to MA. Mass is not a vector. Mass does not have a direction, right? You don't say something is 3 kilograms to the north, right? It is just flat out 3 kilograms. So mass is what we call a scalar. There is no direction associated with it, okay? Force, definitely a vector. You have to give it a size and a direction. Acceleration is also a vector because it has to have a size, 3 meters per second squared, and a direction. Since this guy doesn't have a direction, and there's an equal sign here, these two things have to have the same direction, right, because of that equal sign. So whatever direction your net force is in, your acceleration is in the same direction. So this guy would have an acceleration in the positive x direction because it has a net force in the positive x direction, right? It would also have an acceleration in the positive y direction because it has a net force in the positive y direction. Right over here. This thing, whatever it is, would have an acceleration in the minus y direction. Right? It would also, in the x direction, have no acceleration at all. But what do you know about the x motion? If the acceleration is 0, what could this object be doing? Sitting still or moving at a constant speed. So we don't know what it's doing. Okay? The free body diagram doesn't tell you which way an object is moving, even if you know its acceleration. Right? This guy's acceleration is this way. Doesn't mean the object is moving that way. So we'll talk about that, but you don't know that. But we do know that F and A have to have the same direction. Okay. I'm not even sure which ones. Okay. Right? So if we add up our forces on the x, we're going to get our net x force. Right? That's my F net x. And actually, it's supposed to be in bold, which tells you it's a vector. Boldface is also a vector. Whenever you see something in a physics book that's in bold print, if it's not like a number to a problem, like number 1, number 2, number 3, if it's in the text and it's boldface, that's a vector. Okay? When you're doing it on the chalkboard, kind of hard to make things boldface. So we usually do arrows over top of them. Or we just automatically split things into x and y's and you don't have to worry about it. Okay. All right, so if we add up on the x forces, that's going to give us our net, our total x force, the sum of our x forces. That's going to equal our mass times our x acceleration. Right? If we add up our y forces, it's going to give us our total y force. That's going to equal our mass times our y acceleration. So we just have to think of these two things as being separate entities. Okay. And actually, I'm curious, when you guys do it, do you do off-axis forces and sine, cosine them and You do that? Okay. Okay. We're skipping that. Okay.
Okay, give that a thumbnail approach, because I don't do it on two axes at the same time. I
Oh.
think I might want to.
Oh, okay.
So give that a brief presentation, please.
Yes.
How you equate a slope, or
How I would
like
do it off axis?
If you just had that, I could plot a point and calculate
Okay.
a
Yeah.
slope, right?
Yep. Yep. All right. Yeah, it's actually very easy. So we have this 2 and 2, right?
Okay, right. Well, I
Okay.
do it.
Yeah.
How do
So
I present that?
if you had 2 and 2, it would be going over 2
Right.
and up 2. So if you wanted a point, it would be right there.
Okay.
So that would be, this would actually be your F net, your total F net.
Right.
Okay. This piece is Fx net. Okay. And this piece is Fy net. I'm out of room. Okay. Because we went over 2 and then we went up 2.
Right.
Okay, so what you've got here is you've got this great little triangle. Okay, so I'm going to take that. Can I erase this? Okay, all right. Okay, so we have this triangle where this side is 2, and I do it really badly because they're not the same size. That side is 2, and this side is 2. Okay, and this is our F net. And this guy is our F net Y, and this guy is our F net X, right?
Yes.
So what you can do, if you start with this number, it's basically trig. If you know theta here,
Yeah.
which in this triangle we would know, right? 45, right? So the sine of theta is going to be your hypotenuse, which is this guy, right? Right, over our opposite, which is going to be the y part. Sine. Oh, I'm sorry, I did that backwards. Sine is our F net y. Sorry. Just making sure you're awake, right? Over our hypotenuse, which is F net. So far, so good?
Yep.
So if we want to solve for the y part, we just multiply both sides by the hypotenuse, right? So F net sine theta is going to be the y component. Okay. Now if we wanted to find the x component, what would we do? So if we want to find this side of our triangle, what are we going to use?
X on top.
Yeah, so we want to have the x over here, but what trig function would that have to be? Cosine, exactly. It would have to be cosine. So this is like my school. You put that screen down and you now have no place to write. Yeah.
Yeah.
Right, so same little triangle, that's 2 and that's 2. So the cosine of theta is going to be the adjacent, which is going to be your x, over your hypotenuse, which was your F net. Right? So if you want the x component, it's going to be F net cosine theta. The way the sine cosine works depends upon which angle you're given. Normally you're going to be given this angle. Sometimes they give you this angle, so just be careful about that. You actually have to do the trig. In the lower level textbooks, they pretty much make it always that angle, so that sine is always y and cosine is always x, but that's not always true. Right? If they give you this angle, well in this case it would be the same because it's 45, right? But if it's not, okay? So what you'll see is they can do it 2 ways. They can tell you your net force is 2 in the x direction, right? And then 2 in the y direction. Or you can say your net force is the length of this side, which is what? 2 times 2 square root of 2? Yeah, right. Hold on. Yeah, no, I'm just going to pull up the screen because I'm out of, yeah, it's, not on. It says it's off. Now it's flashing at me that it's on. That might not work either.
FaceTime is some practical problems.
What's that? There it goes.
Problems.
So you're going to either see 2 newtons, like I said, I would have I hat in the x direction, and 2 newtons in the y direction. Or you're going to have, is it 2 square root 2, is that what we decided? 2 square root 2 at theta equals 45 degrees. And those 2 things are telling you exactly the same information. This one is telling you the side of this triangle is 2 root 2, and it's telling you this angle is 45. This is telling you you're over 2 and you're up 2, but they're both taking you to that same point. So if you're given this one, you can do trig to find this side of the triangle. If you're given this one, you have to be given an angle or something else. Sometimes you're given the other side, but usually you're given the angle.
And the length of that vector is going to be 2 times the square root?
Well, yeah, it's going to be 2 squared. It's a Pythagorean theorem, so it's going to be 2 squared plus 2 squared square root of that. That's your hypotenuse. So the square root of 8 in this case, which is 2 root 2, right? But that's because I happened, just by sheer coincidence, to pick pretty numbers. If this was, let's say, give you guys a hard one, see if you can do it in your head. Let's say instead of 2 and 2, we had 5 in the x direction and a minus 6. And a 6 in the minus y direction. Let's say we have that one. That's an and right there, right? So 5 in the x direction and a minus 6. So we'd have to go over 5, and then we have to go down 6. Right? So this side is 6, and this side is 5. And that's the information that the top one is giving you, right? If we want to find the length of this side, we'd have to do 5 squared plus 6 squared and take the square root. Which? What is it? 5 squared plus 6 squared square root?
7.8.
Really? Okay, 7.8. Because that was 5 squared plus 6 squared square root. All right? So then it would be 7.8. That's not enough. You need to know where it is. So you have to be given some kind of angle. So if you wanted to get theta, right, how are you going to get theta? Inverse tangent, right? You could do an inverse cosine or sine, but then you're using a number that you've calculated. So if you got that wrong, it's propagating. So let's just say we don't know this guy. All right. Tangent of theta is going to be opposite over adjacent, right? Yeah, thinking back to tangent. It's going to be opposite over adjacent. The opposite over adjacent for tangent, right? So our opposite's going to be 6, our adjacent's going to be 5. And then you would do an inverse tan, and what are we going to get? Anybody? You used to know that off the top of your head. I have a calculator, I think.
I got it.
You got it? What is it?
6 with, what's 5? 6 over 5? 50.1.
I'm sorry?
50.1.
Okay. So 50.1. Right. So you should be able to go back and forth. You can either be given a magnitude, a total force at an angle, or you can be given the x and y of that triangle, and then it's trig. Which, you know, you'd think, oh, cosine, sine, tangent, you know, you'd think like first-year engineering students should be able to do that. No. No, they can't. Some of them really can, but others, no. And they will build your bridges someday. And that's the scary thing. What's that? You spent a lot of time on the sine cosine? Yeah. The ones who've had high school. Yeah.
I don't teach separately.
Right. Well, I would say most of the ones who've had good math background are fine with it, but the ones who've never had the math and have never had the physics before,
Physics, they've never saw sine, cosine,
yeah, they can't do sines, cosines, and tangents. Yeah.
theta. So I tell them, I said, I'm just teaching you how to use those buttons on your calculator. So when you can't take trade.
But what kills me is that, yeah. What did you say? You're teaching them buttons in their calculator, but what?
I said, a lot of kids I have never saw sine, cosine, tangent. Some of them, like,
Yeah.
So I said, I'm going to show you how to use them on your calculator. This is physics. I'm teaching you how to use this, how to apply that formula. If you want to know where sine, cosine, tangent came from, take trig.
Go take trig. What happens then, what I find that happens in my class that can be bad then, is if they memorize that sine gives them the y component and they memorize that cosine gives them the x, they will periodically, instead of given this angle, they'll be given that angle, or, yeah, and then they're stuck because they are automatically using sine for y and it's not necessarily true. So we go through it a little bit simply because my students, their background is lacking. I'm sure if they were at Harvard, they'd be fine. But, you know, my kids aren't at Harvard for a reason. Here with me. But did that do it for you in a thumb? I mean, was that a good summary? Okay. Okay. All right. All right. So Jerry, I got to ask, when he came to work with you, did you have to interview him?
Who's him? No, he doesn't.
I don't work as.
Oh, okay, okay.
No,
So that'd be fun. All right.
We gotta hit the pause button for a second.
Uh-huh. Hold
I'm
it.
going beyond the scope of what we were just doing.
That's okay, because that was beyond my notes, so we're good.
If you're given the, I know, but I think this is relative for everybody.
Okay, if you're given,
If you're given the angle of your vector,
Mm-hmm.
and you know one vector, how do you figure out the other one?
Right. Oh, sine, cosine.
hold on, I lost my chalk. But yes, what Jerry is saying, yes. So if you're given, you're saying if you're given what? Are you given,
Say you're given the angle.
okay, so,
Say it's some degree.
okay, 50 degrees.
Okay, and
not
you're
quite.
given one vector.
You're given
Which one? A side, or this one?
Given the hypotenuse.
Okay, so let's say this guy is 6 newtons, okay?
Okay, what do you do? How do you find the other?
The other
vector,
2 sides,
Right.
okay? All right. We will call this side the opposite.
Right.
We will call this side the adjacent. And we know that the sine of 50 is going to be the opposite over the hypotenuse,
Right.
right? So it's going to be opposite over 6,
Okay.
right? So if you want to find the opposite, it's going to be 6 times sine 50,
Okay.
right?
Okay.
And then if we wanted to do the other guy, we would know cosine is adjacent over hypotenuse, right? So if we wanted to find the size of the adjacent one,
Work through the formula.
yeah, yeah, yeah. And it could even be something really weird where they're giving you an angle and, you know, that side, and you could still figure it out, but I've never seen them do that. It's usually this and the angle or that and that. Yeah. We know our acceleration has to be in the x direction, okay, because we know that our sum of forces has to equal ma. This doesn't have a direction, so whatever this guy's direction is, the a is going to have the same direction, right, because of that equal sign, that little equal sign there. It tells us that the number, whatever number is on the left-hand side has to equal the number on the right-hand side. It also tells us the direction of whatever is over here has to equal the direction of whatever is over here, okay? So our F net and our acceleration are to the right. That does not tell us if this guy is moving to the right, okay? Because, for instance, let's say we've got a little person here, and they are walking, okay? And let's say they are walking towards the door, that way. So that's a walking arrow, not a force arrow, okay? If they are walking this way towards me and their net force is towards me, it would be like walking towards the door and having somebody shoving you from behind, okay? So that person is going to be speeding up, right? But let's say this person were walking the other way. You're trying very hard to walk this way, but you've got a big force pushing you that way, right? That person's going to be slowing down, right? Okay. We don't know which one of these is happening to our dot, whatever it is, right? It could be moving to the right and speeding up because the net force would be helping it. It could also, whatever it is, be moving to the left and something is slowing it down. Okay, so when you look at a free body diagram, you don't know which of those is going on. Just by looking at a dot, you don't know, is that somebody walking towards the door being shoved faster, or is that somebody trying to walk over there and people are pummeling them trying to stop them, right? So they will be slowing down. Either way, they're changing speed. So if they're moving in the same direction as their net force, they're going to pick up speed, right? So if you're standing on, I have a skateboard, we're going to pull the skateboards out later. But if you're standing on this skateboard and you're rolling that way and somebody's shoving you that way, you're going to speed up, right? If you're rolling that way and somebody starts shoving you this way, you're going to slow down, okay? So either of those could be happening to our little object. Sometimes your problem will tell you. A lot of times your problem tells you. But you can't just figure it out from looking at your picture. Okay. Mine's an F8. Okay. All right. So if our force is in the direction of motion, right? If our force is in the same direction that the object is already moving, that object is going to speed up. Okay? So if I'm moving this way and my net force is pushing me this way, I'm going to start going faster. Okay, that's what the top one's saying. The bottom is saying if I'm moving this way and the force is pushing me that way, I'm going to slow down, right? The force is trying to stop me. Okay, that's what this is saying. So if our net force is opposite our motion, we're going to slow down. Okay? So if we're trying to walk that way and our net force is trying to push us this way, we're going to slow down. Okay? Okay? Right? Eventually we would stop. And then if it keeps pushing on us, we'd end up going back the other way. Right? Maybe talk about that later. If our net force is 0, if our object is moving, it's going to keep moving with no acceleration. Right? If our object is at rest, it's going to stay at rest. So we'll talk a little bit more about it later when we get to acceleration. You can kind of see the numbers, the way the numbers work out. And then you're like, ah, the numbers work. It makes perfect sense. You guys with me? Make sense? Yep. Right? Okay. Same thing is true up and down, right? If an object is moving upward and the net force is down, so for instance, let's say you throw a ball into the air, the main force on it, the net force, is gravity, and gravity pulls down. It's trying to move that way. The force is trying to pull it this way. It's going to slow down on the way up, right? If it's falling towards the earth, now it's moving this way and the force is this way. That guy's going to speed up. Okay, so it happens up and down and sideways. Okay. What time do we even go till? We go till 11 o'clock. Okay. All right. I know, time flies when you're having fun. Vectors are fun. It makes it go so fast. All right. Okay, so let's go revisit our Newton's third law. Okay, on my screen, the Earth looks oblong. All right, so we've got a table that's sitting on the Earth. Okay, however hard the Earth pulls on that table, the table actually pulls back just as hard on the Earth. So if that table is 20 Newton table, okay, 100 Newton table, if it's a 100 Newton table, that means the Earth is exerting a 100 Newton force on it and pulling on it. But Newton's law tells us that somewhere out there, there has to be a same size force going in the opposite direction, right? So if the table is being pulled by the Earth is going to pull back on the table. So in Newton's third law, there's two objects always involved. One is exerting a force, the other is exerting the opposite force, okay? So for gravity, gravity is pulling on you, you're actually pulling back on the Earth, okay? However hard gravity is pulling on you, you're pulling back just as hard. Okay. we're pretty small compared to the Earth. So for us, that's a pretty big effect. We notice it. The Earth doesn't really care, you know, that we're pulling hard on it because it's a pretty big object. It's a pretty small effect, which we'll talk about as well. But we have to talk about a couple different types of forces. Now, if we look at this table, there's like little slivers of chalk up here and one good piece. Hang on to it. Right, there's my table, it's a dot. It has gravity pulling it down, that's our force down. Right, gravity is pulling you towards the center of the Earth. If I just draw this from my table, can these forces add to 0? No, because there's just one force here. Right? It can't add up to 0. Okay? So that tells us either two things. One is that this object is accelerating, my table is accelerating, or I've forgotten a force. Okay?
Chances are it fell on a shipping plane.
All right, so our gravitational force is one of the main forces that we're always going to be working with. Gravity pretty much affects everything, right? And gravity acts between any two objects. You exert a gravitational force on the chair you're sitting in, and that chair exerts a gravitational force back on you. Any two objects with mass exert gravity on each other. But you have to have a huge mass before it's noticeable. So like a planet, a moon, right? So even though you're gravitationally attracted to the person next to you and there's an equal and opposite force from them back to you, it's not very noticeable. But in the physics world, it's a cool bar pickup line, you know? But yes, there is a gravitational force between any two objects that have mass. Okay? It just doesn't show up unless it's a big one. You don't even notice it. All right, so our table here is missing a force. So let's look at what's going on, for instance, if we have a box on our table. Okay. Well, actually, oh, don't drop my chalk. My good piece of chalk. My table, I'm going to draw it out. Okay, and I've got my little box on it. Okay. If I look at my box, gravity is pulling it down. That's your weight. So you could write a W for weight. You could call it gravity. You could call it mg. You could call it big G. I'm going to spell it out. Gravity pulls that guy down. There has to be another force, otherwise that box would be accelerating. Okay? So the other force is that the table is pushing up on it. Okay, so this is a normal force. And it is occurring, in this case, between our table and our box. So I'm going to call it table slash box. That's a slash, not a divide. Just a table slash box. Okay? All right. If our box is not moving, how does this arrow in size compare to that arrow in size? Same, right? They're the same. Okay? These are not a Newton's third law pair. Okay? They may be the same size, but they are not, by Newton's third law, a pair. Newton's third law says if the Earth is pulling on the box, then the box is pulling back on the Earth. So if we want to see the pair, Newton's pair to this, we actually have to draw the Earth down here. Okay? And we would actually see that there is an arrow on the Earth, also called gravity, right? And it is pulling back on this box just as hard as the box is pulling on it. These two are a pair, okay? Newton's third law pairs never, ever, never show up in the same object's free body diagram. If this is one of your Newton's third law pair, you will not find the other one in the same picture. You have to go to the other object, and then you find the pair, okay? So the normal force, that is how hard our table is pushing on our box. Where are we going to find the pair for that? Where's the equal and opposite force for that?
The weight of the box.
On the table. Now the weight of the box is between the box and the Earth.
Oh, okay.
Yeah. If the table is pushing on the box has to be pushing back on the table. So if we were to draw a free body diagram for the table, we would see this is where it's getting ugly because I now have a table in here. All right, I'm going to draw it to the side. This is going to be my table's free body diagram. It is going to feel the opposite of this normal force. It's going to feel it pushing it down. So it's going to feel the normal between the table and the box. Box. All right? Those two are a pair. They don't show up in the same object's force diagrams. These two might coincidentally be the same size. One might be 5 Newton, one might be 5 Newtons. Doesn't mean they're a pair, okay? Newton's pairs, from the third law, his pairs are always between the two objects that create the force, okay? So if we want the pair to gravity, the Earth is pulling in the box, we have to go down here and see how hard the box is pulling back on the Earth. These two are a pair. So normally when we're doing these, we kind of like, those two are a pair. This guy's pair is going to be over here in this guy's picture. Okay, so his pair is down here, same size, different direction on the other object. Okay? And if you think about it, if you're the table, you feel that box pushing down on you. Right? You're aware there's an object sitting on you. Right? So you're feeling the opposite. Right? The box is feeling something holding it up. Okay? So these two are a Newton's third law pair. These two are a Newton's third law pair. Okay? All right, our tables diagram over there, we're missing something. Because can that one force possibly add to 0? No. All right, so what are we missing for our table? We know we have to have an upward force because our table's not going down, right? It's not accelerating downward. So what's our upward force? Sorry. There. Yeah, and what kind of force is it? Gravity's pulling it down, so we're going to have to put that in there.
Normal force.
Normal force. There's another normal force. Right? This guy feels a normal force between the table and the Earth. If we wanted to find the pair of that, where would we have to look? Which diagram would the pair show up in? Well, if the Earth pushes on the table, what does the table push back on? The Earth. So we would actually have to look here. In the Earth's free body diagram, we would see the opposite force. It's being pushed by the table. So down here, we're going to have a normal force between the table and the Earth. And this guy, I'm running out of little symbols, we're going to make him a squiggly, is that guy's pair. Okay? So however hard the table pushes up on the box pushes back just as hard on the table. Right? However hard the however hard the Earth pushes up on our table, right? The table pushes back just as hard on the Earth. Okay? However hard our box pushes on our table, right, it pushes back just as hard. So there's always a third law pair. It will never be in the same picture. You have to look at the other object to find it. This is also a common mistake because my students want to say these two are a pair. And they're not. Okay? Technically, they may be the same size, but they're not a pair. They're not a Newton's third law pair. Okay? His pair, you would have to go to this guy's picture to find it. Right? This pair, you'd have to come down here to the Earth to find it. Okay? If we wanted to be technically correct, somebody said it, gravity is also pulling on our table, right? So really, we should have another downward arrow here. That would be gravity. If you're looking at the table, gravity is acting between the table and the Earth. Right? So this would be gravity between the table and the Earth. If we wanted to find the third law pair for that, where would we have to look? The Earth, right? If this is the Earth pulling on the table has to pull back on the Earth. So this guy is going to have another upward arrow, and this is going to be the gravity between the table and the Earth. All right, and this guy was the box in the Earth. Okay. All right, so the trick with your third law pairs is they will never, ever, ever, never, ever show up in the same picture. Okay? So these two are not a third law pair. Okay? You have to have two objects. One of them will have the force. One of them will have the equal and opposite force. Right? So he has the force. Right? The equal and opposite force is on the other diagram. Right? He feels the force. The equal and opposite force is in the other diagram. Okay? He feels this force. The equal and opposite is in the other diagram. Forces occur between two objects. Right? Each of those objects gets part of the pair. How we feel about that? Normal force equal to mg, because for whatever reason they want to do that. It is not always true. All right. All right, so in our Newton's laws pair, one force somewhere out there, the other object has the equal and opposite force. Same force, but in the opposite direction. Right? Yay, Katrina. Yes? We're good? Okay. Let's see. Normal force. We're all looking at you now. Okay. No pressure, but we're all looking at you. All right. Another good, we're going to use our spring scales one more time. You want the blue one out. I'm going to give, I got 12 magnets. So each pair, I'm going to give you, you want 2 blue scales. We're going to have to share maybe. I'm going to give you 1 magnet. They're really strong magnets. So don't get it next to anybody else's magnets because it'll smash your fingers and it hurts and then you curse. Oh yeah, they hurt. Yeah. My kids were laughing at me as I was packing them because they kept smashing my fingers. They have bruises on my thumbs from them. So just be careful with them. And hold on here. Once bitten, twice shy, right? Okay. They look innocent enough.
Right.
Trust me. They're
But there's
evil.
a force to them, right?
What's that?
There's a force to them.
There is going to be a force on them, yes. Yes. Yeah, oh yeah, you might want to move your iPad. I don't know how they affect. There we go. I feel like I'm shedding. Okay. I feel like there's that one. Can you do what? You can do whatever you want. Did you get it? B? But did you do it twice? Oh, see, it's the key B. The key B does it. All right, so I take back my denigration of PCs. B. All right. All right. Here you go. Can you hand that to him? Okay. All right. You're going to put the magnet on one of your blue scales, and on your other blue scales, you're going to hook a paper clip. Oops, you just need one. Yeah. Did I give you guys a magnet? Okay. Did I give you a magnet? No. Okay. Ready? Sorry, I thought you were looking at me. Just throwing it at you. Yeah, what you're going to do is you're each going to, one of you, got one of these guys. You're going to hold on to the loop end, the hook end. One person's hook is going to have the clip, the paper clip. And it's easiest if you just do it like that, okay, instead of trying to actually clip it on there. And the other person's hook is going to have the magnet. And what you're going to want to do is lay them on the countertop so that you're both reading the same units, either newtons or pounds. Okay? Right, you want to, when it moves, when that clip and the magnet jump together, you want to be holding this part stationary. Okay? So you're going to have it sort of.
So I'm hooking the magnet on to the
ring
Yeah,
along
the magnet, it'll hook on all by itself. Yeah. It'll go on all by itself.
Okay.
So you're gonna bring them closer together, but you wanna hold on to this end so that when they jump together, you get a reading on your scale, okay?